Okay, good morning, everyone. It's my pleasure to kick off the memory vendors section of this forum. The title of my talk today is Expanding Beyond Limits with CXL-based memory. My name is Jonathan Prout, and I'm a Senior Product Planning Manager at Samsung Electronics. So in terms of an agenda, I'm going to touch on some industry trends and challenges that are motivating the use of CXL-attached memory. And also talk a bit about CXL as it relates to Type 3 memory devices and explore a few use cases that show the value of CXL attached memory. And then finally, I'll discuss some real-world products that we already have, which is our CXL-based memory expander, as well as a scalable memory development kit for managing heterogeneous memory systems. So just to motivate this talk a little bit, in recent years, the growth of technologies like artificial intelligence, machine learning, cloud computing, all of this has led to massive amounts of data being generated. So the rise of data-driven technologies has also triggered the need for more powerful computer hardware architectures. So we're seeing more cores being integrated onto single processors in order to create more powerful, more capable processors handling all of this data intensity. But the problem with this is that memory bandwidth and memory density are lagging behind increasing CPU core counts, so the performance between memory and the CPU is beginning to diverge. So the insatiable demand for memory density and bandwidth is pushing the limits of existing memory technologies. Conventional DRAM design limits the scaling of memory capacity beyond a certain range, so this is requiring a new interface, namely CXL. And so what's more, the rise of AI and big data has fueled the trend toward heterogeneous computing, where multiple processors of different kinds are working in parallel to process these massive volumes of data. And so in light of these trends, next generation interconnect technology like CXL is essential for heterogeneous computing and composable infrastructure to enable efficient resource utilization. And so just to touch more specifically on this challenge of meeting memory demand, this chart shows the trend in CPU core count and memory channel bandwidth per core over the past decade. And as you can see, the memory channel bandwidth per core has essentially been flat. It's even been slightly reduced, maybe at 75% of what it was a decade ago, whereas CPU core count is up maybe 3x. So without some kind of innovation, this gap will continue to get larger, and this is why we at Samsung view CXL, and I actually want to echo what Willie said, it's not necessarily an evolutionary technology, it's more of a revolutionary technology. So just to touch a little bit about CXL, since this is a CXL forum, as we all know, it's a cache-coherent CPU to device interconnect technology. It's on the PCIe physical layer. It's optimized for high speed and low latency. So the transaction layer, it's made up of 3 dynamically multiplexed subprotocols on a single link. These are CXL.io, CXL.cache, and CXL.mem. And so when a CXL device is connected to a CXL host, it's discovered, enumerated, and configured via CXL.io. CXL.cache, it enables devices to access processor memory, and CXL.mem enables processors to access CXL device memory. CXL.cache and CXL.mem, they're stacks optimized for low latency. And then on top of that, we have 3 different device types that CXL defines. And the one that we're most interested in today, of course, is CXL Type 3 devices, which use the CXL.io and the CXL.mem protocol. So what exactly are Type 3 devices? A Type 3 memory device has a controller and attached memory, but unlike Type 1 and Type 2 devices, Type 3 devices don't have compute logic on the device side that can modify the content of the memory. Rather, the CXL Type 3 device enables different types of memory media to be attached to the host through the CXL link. So an important point to note is that the memory attached to the CXL device is mapped coherently to the system address space. So this means that the CPU and the device see the same data when they need to access it. The CXL host has a home agent serving as a manager which uses CXL.io and CXL.mem protocols, And the CXL.io protocol is used for discovery, configuration, and management, whereas CXL.mem is used by the home agent to access the attached memory. Also, CXL.mem transactions are byte addressable, and it uses load store transactions just like DDR memory, so the attached CXL memory looks like native attached DDR memory to the end application. So the benefits of coherency is that CXL host and the CXL device can work on the same shared data and are guaranteed to see the same copy of a memory location. The home agent does not allow simultaneous changes of the data, and once a change is made either by the host or the device, the home agent ensures that all copies of the data remain consistent. So we'll take a look on this slide of an example of how memory can be expanded using CXL memory. So the traditional way of adding memory capacity and memory bandwidth in a system is increasing the number of DDR channels or by increasing the data rate of the memory, but these come with drawbacks, increased complexity, reliability issues, increased PCB layer count, all sorts of things. So CXL gives us the flexibility to attach memory in a number of different ways. You can attach it to a PCIe slot, you can attach them to NVMe drive bays, and eventually even we may see memory appliances. So if we look at this picture, memory, on the left side we have a hypothetical system. It has 8 DIMMs, and if we, or 8 channels, and if you have 2 DIMMs per channel at 512 gigabytes, then we have an 8 terabyte system. When you look off to the right side, in addition to the 8 DDR channels, we also have 4 CXL links, each supporting up to 1 terabyte of memory. So this is expanding the total system capacity up to 12 terabytes. And like I said, what's unique about this is that we're not increasing the number of primary CPU channels. We have that flexibility to add it in a number of different ways for more cost-effective memory expansion. So graphically, I just wanted to show this, these 2 use cases of capacity expansion and bandwidth expansion. These are not mutually exclusive, but I just wanted to kind of draw out some of these use cases a bit more separately. So first, when we look at capacity expansion, users can add memory capacity via CXL, which allows them to consolidate memory on fewer servers to reduce memory over-provisioning across servers. So this reduces the number of servers required and results in TCO savings at the system level. And this would be particularly advantageous for high memory systems like in-memory databases, in-memory computing applications that require high capacity. So like I show here, instead of over-provisioning, we can consolidate onto maybe 1 or fewer servers by using these high capacity modules. And that's sort of graphically illustrated there by the larger orange CXL memory on the screen. And then second, and related to that, is bandwidth expansion. In a similar vein, we could have memory modules with lower capacities to achieve a higher bandwidth per gigabyte ratio. So in this case, you're just trying to attach as many devices as you can to increase the aggregate bandwidth to the system. And this is shown here by the sort of smaller CXL memory modules to indicate that we're really looking for bandwidth expansion in that use case. Okay, and another important feature I want to touch on with CXL as it relates to CXL memory is switching. In CMEC this morning, I went over this a bit. But looking back, CXL 1.1, it addressed the node level interconnect challenge. CXL 2.0 kind of increased the reach 1 level higher to the rack level, at least for memory, so we could do memory pooling at CXL 2.0. Left side of the slide, we can see an example of memory expansion through a CXL switch where multiple CXL Type 3 memory expander devices can be connected through a switch to a single host. We can fan this out by attaching numerous switches to a CXL host, and then off of each of these switches you can continue to add more CXL memory devices. This would be sort of a fan-out memory expansion system. And then on the right side, we have an example of memory pooling where you have multiple hosts can access pooled memory through a CXL switch as needed for a certain period of time. So this increases the overall system efficiency, and it allows dynamic allocation and deallocation of memory resources. And a couple of use cases where switching will play an important role is in memory tiering and also memory pooling. So first, with memory tiering, we can dramatically expand memory capacity cost effectively using various types of media. So for memory applications, not all data is hot and needs to be stored on main memory. We can use offload software to tier the data and other media based on policies to achieve higher efficiency of memory usage without compromising on the workload performance. In many cases, too, this sort of next tier media, it's not as performance sensitive, so we can imagine much of this could be placed behind a switch. The second here is memory pooling. So instead of attaching CXL to a particular server node, we may have a configuration in the future where we have a memory box, and perhaps this memory then would be accessible by various hosts within a server rack. And we see this as being a very compelling use case to really improve the utilization of memory and, again, be able to achieve greater cost savings and better utilization of the memory. So next, I want to turn now, probably of most interest and relevance for this particular conference is looking at actual hardware that we've developed at Samsung. So in May of 2021, Samsung introduced the industry's first CXL Type 3 memory expander prototype. This used an FPGA and has 128 gigabytes of DDR4, CXL LimitsWith of by 16, and comes in both E3.S and AIC form factors. Over the past year, we've shipped over 100 of these samples to our partners and customers across the ecosystem. The memory expander prototype has already been tested with multiple end customers using real applications and workloads. So at Samsung, we're making a very serious effort to support the emerging CXL memory ecosystem, and we view this year and next year as being particularly important in helping our customers and partners adapt to the memory architecture changes that are being brought about by CXL. And so sort of the next phase of that POC that we've had for roughly a year is our ASIC-based module that will be used for mass production. So we introduced this memory expander. It's going to have an ASIC controller, and it's poised to pave the way for the commercialization of CXL memory technology. It'll be delivered in an E3.S form factor, and it's suitable, of course, for next generation high-capacity enterprise servers and data center workloads. So this latest module, it comes with up to 512 gigabytes of DDR5 memory, and this will enable servers to expand their memory capacity to tens of terabytes and increase the memory bandwidth to several terabytes per second. The memory expander uses a by-8 interface to connect the CPU, and it will have a maximum bandwidth of 32 gigabytes per second. So importantly, this CXL DRAM memory expander will be available for early evaluation this quarter. So we're literally just weeks away from being able to deliver first samples of this to some of our partners. And this will be an important step in enabling our partners to move from validating the CXL protocol and doing initial performance tests limited by the overhead of the FPGA and getting to a better real-world understanding of CXL memory with an ASIC controller. And then on the software side, Samsung introduced an open source CXL software solution. We call it the Scalable Memory Development Kit. It's a collection of software tools and APIs that enable the main memory and CXL memory expander to work together seamlessly in a heterogeneous memory system. And so just to quickly go through the software stack here on the screen, at the bottom, or near the bottom of the blue rectangle, we have the memory pool management layer. And this is sort of an abstraction layer that separates the management of normal memory, which is natively attached DDR, from CXL memory. Next, the intelligent tiering engine supports different use case needs by allocating the appropriate memory according to capacity, bandwidth, and latency priorities based on the application requirements. And then finally, the compatible API enables system developers to easily incorporate CXL memory into advanced systems without having to modify their existing application environments, and thereby accelerating CXL ecosystem enablement. Alternatively, we also provide an option for users to perform high-level optimization by modifying the software application to take full advantage of the underlying memory technology characteristics. And so we view SMDK as an important step to driving the CXL memory industry forward, and we're proud to be publishing this as an open source software for the industry to utilize. Version 1.1 is available today for download on GitHub. And finally, my last slide, I just want to wrap up with an application benchmark test that we've run using our FPGA-based POC and the SMDK that I just introduced. So for our test scenario, we ran one Redis node on a single system using 32 gigabytes of main memory DDR5 and 64 gigabytes of CXL attached DDR5. This 64 gigabytes of CXL memory was implemented with our POC, as I mentioned. And we also ran Redis on 3 nodes, each with 32 gigabytes of main memory over a cluster comprised of 2 systems. So in this way, we were able to test a scale-up configuration using CXL memory versus your traditional scale-out method. And what we saw when we monitored the bandwidth on this application for 128 bytes, 4 kilobytes, and 1 megabyte chunk sizes was that for both set and get operations, for normal chunk sizes of 4 kilobytes, the performance was about 2.5 times better in the scale-up configuration as opposed to the scale-out configuration. I do just want to highlight this was done using our POC with an FPGA. As I mentioned, we're very close now to be releasing samples of our ASIC-based product, and we'll be continuing to do application tests, and we do expect, of course, that they'll be significantly better than we have here based on the fact that we're using an ASIC rather than an FPGA. So, we're very excited about the developments that we're doing at Samsung with CXL memory. We very much have a strategy to promote early this ecosystem because we think that it'll benefit not only the memory industry, but of course all of our partners, because there's a tremendous amount of data that we're all trying to keep up with, and we're really trying to close that gap between the increasing core count of CPU and closing that gap by providing a memory solution like CXL memory.